Hi, everyone. Welcome to what will be our asynchronous portion of Lecture 2. So a reminder that you should be watching this video before class, class on Thursday, and this will cover a lot of the conceptual things that I'll go over a little bit in class, but this is meant to cover the bulk of the material. Okay. And so if you'd like to read more about any of these, you can see our textbook, PDF by Flowers, and it is chapter 10, sections 10.1 and 10.2. Okay. All right, so in class on Tuesday, we talked about basically what intermolecular forces are, how we define them, the difference between intramolecular forces and intermolecular forces, and a reminder that this chapter is going to focus on intermolecular forces, or IMFs, as I will abbreviate them throughout. And these things will determine a lot of characteristics about our molecules, be it the state, solid, liquid, or gas, or properties, particularly of liquids such as viscosity, vapor pressure, boiling point. Okay, and also a reminder that within those states, we talked about how there is essentially an inverse relationship between the increasing kinetic energy and the increasing intermolecular forces. So that is to say the crystalline solid, a solid like a salt, that is dominated by ion-ion attractions between atoms is going to have the lowest kinetic energy and the highest intermolecular force. Liquids will be intermediate between those two things, and then gases will have the highest kinetic energy, while as they will have the lowest intermolecular forces. Okay. Also a reminder of the three different types, or I guess four different types that we'll talk about in this class. The first three are the main ones. These are all different types of van der Waals forces. So all of the forces, these four forces listed here are all van der Waals type forces. The weakest of which is dispersion forces, sometimes called London dispersion forces. We also have dipole-dipole interactions, which is our intermediate strength intermolecular force that is found in molecules that contain a dipole, basically difference in negativity or positivity caused by a difference in electronegativity. And then we also have hydrogen bonds, which are an extreme case of a dipole where you have a hydrogen bound to either nitrogen, oxygen, or fluorine. Okay, something that I'll mention that we're not going to go over a ton in this class, but you can also have ion-dipole interactions. So if you have one molecule that has a dipole, it can also interact with an ion. And then you can, of course, also have ion-ion forces, which are things that like hold salts together. So if you have like sodium chloride, the sodium would be positively charged, the chloride negatively charged. They're held together because of the attraction of the positive and negative. Okay. All right. So I want to take this portion of lecture to go through some of the specifics for each of these. So first, we'll start with, again, the weakest intermolecular force called dispersion forces. And these are going to be present in all states of matter. Okay. Because the electrons of an atom or a molecule are in constant motion, at any moment, an atom or molecule can develop a temporary and instantaneous dipole if its electrons are distributed asymmetrically. Okay, and so that's what really causes these dispersion forces. And the larger an atom is, or the larger a molecule is, the more dispersion forces it will have because of the larger electron cloud surrounding either a particular atom or within a molecule itself. Okay. And so a phrase that we use to describe these is polarizability, a molecule with a charge cloud that is easily distorted, or an atom that is large, heavy, has a large electron cloud, is said to be easily polarizable, okay? And it would have larger dispersion forces than smaller atoms. Again, think of your nitrogens, your oxygens, your fluorines. Those are small. We would call them non-polarizable, meaning that they don't have dispersion forces, but tend to lean towards things like dipoles. Okay. With dispersion forces, because everything is capable of having dispersion forces, what are the characteristics of molecules that have intermolecular forces dominated by these dispersion forces? And so some characteristics there are that they tend to be of a single element. So for example, if you look at the different halogens, so fluorine, chlorine, bromine, iodine, and astatine, you could see that as they get larger, the melting point increases as well as the boiling point. And that is because they have a more polarizable electron cloud, making their dispersion forces greater and having an effect on the physical properties then of these molecules. Okay. Also characteristic is these molecules contain bonds that are nonpolar with regards to electronegativity. We'll go over in a review of electronegativity in class a little bit on Thursday. A good example of these is hydrocarbons. So anytime you have a bond between a hydrogen and a carbon atom, we would consider that nonpolar. They also may contain polar bonds, but in a symmetrical fashion. And so a classic example of that is called carbon tetrachloride, CCl4 here, where there are polar bonds, but all of those polarities cancel out in different directions. And so they cancel out to zero, meaning that this molecule's intermolecular forces would be dominated by dispersion forces. Okay. And so that's dispersion forces. Next up, we have dipole-dipole attractions. Hopefully you recall from the chapter covered in Gen Chem 1 that the molecular geometry will have a large effect on a molecule's dipole. And so in our example here, we have just a diatomic molecule where we have one atom that is more electronegative, shown here in the blue, and then one that is more electropositive, we would say, or you could also say it is less electronegative, and that would be shown in the red in these diagrams. Okay. And we would denote these with partial positive and partial negative charges. We use the lowercase delta here. So if you hear me say delta, with regards to intermolecular forces, it's usually with regards to the partial positive charge. So we have partial positive and partial negatives, and this creates what we would call a dipole. Okay. And so the polarities are determined by the electronegativities of the atoms bonded together, as well as the geometry. In the case of these diatomic molecules, they obviously only have linear direction, and so it's pretty easy to find the dipole. But as molecules get more complex, it might be more difficult to determine the dipole, and that's something that we're going to practice in class. Okay. The effect of dipole-dipole attractions is pretty clear when you start to compare things. So if we compare the two molecules, HCl and F2, they both consist of the same number of atoms. They have close to the same molecular mass. However, if we are looking at 150 Kelvin, which is pretty cold, that's like minus 100-ish Celsius, probably about minus 150 Fahrenheit, though I don't know exactly. But the dipole-dipole attractions there between HCl is sufficient to cause them to stick together and form a liquid, whereas in fluorine, where its intermolecular interactions are dominated by London dispersion forces, that remains a gas at that temperature. Okay. And so again, here are some things to help you identify molecules that might have their intermolecular forces dominated by dipole-dipole attractions. They must contain multiple elements, so that would also mean different elements. They can't just be all oxygen or all sulfur or all nitrogen or all carbon. They have to have multiple elements. Okay? They must contain polar bonds. And so again, we'll review electronegativity some in class, but you essentially need differences in electronegativity to have polar bonds. You also need to have polar bonds that are non-symmetrical in fashion. So we can contrast our carbon tetrachloride with carbon-hydrogen trichloride. This is also known as chloroform. And so these polarities would no longer cancel out to 0, and this molecule would have a clear polarity, or dipole is another thing we could call that. Okay. Great. Last up that we'll talk about in this video is hydrogen bonding. This is essentially an extreme form of a dipole-dipole interaction, and it is so extreme that we identify it as its own thing. And so a hydrogen bond will occur when hydrogen is bound to one of the 3 most electronegative atoms, nitrogen, oxygen, or fluorine, what I like to dub the NOF monster, NOF. And if you look at a periodic table, you'll see that all of those elements are towards the upper right-hand corner. Okay. These hydrogen bonds are the strongest intermolecular force that we'll really cover, but you should keep in mind that they're still only about 5% to 10% as strong as an intramolecular bond. So the bond between this oxygen and hydrogen, for example, is going to be about 90% stronger than this intermolecular bond between this hydrogen and this oxygen, right? Right. And so in order to have a hydrogen bond, you need a hydrogen bond donor and a hydrogen bond acceptor. And so typically the hydrogen bond donor will be either an NH, OH, or FH. And the hydrogen bond acceptor will have some sort of lone pair of electrons that are available that the hydrogen atom can interact with. So for example, in this water molecule, again, we have this oxygen and this hydrogen that are bound together. This would be our hydrogen bond donor. And then if we were to draw a Lewis structure, this water molecule would have 2 lone pairs available that could act as hydrogen bond acceptors of that hydrogen. Okay. And water in particular is an exceptional case of hydrogen bonding because it can donate 2 hydrogen bonds as well as accept 2 hydrogen bonds at the same time. Something that you would see with this water molecule here where it has 2 hydrogen bond donors and 2 hydrogen bond acceptors. Okay. All right, so that's it for our intermolecular forces asynchronous portion of lecture. I hope it was informative. If you have any emails, feel free to, or any questions, feel free to email me. Sorry about that. Otherwise, have a great day, and I will see you in class on Thursday. Take care.